Lesson 55, we cover some additional types of permutations. We have so far done permutations where we put things in a line, in a row, and we've done ones where we put certain conditions or restrictions on some of those places. Today we'll talk about what happens if we put them in a circle, or what happens if we have some that look exactly alike, so we can't tell them apart, and we want to know how many ways are there to arrange them that actually look different. Those will be called distinguishable permutations. Our starting point, if I have 4 students and I put all 4 of them in a line, how do I set that up to solve that, Kane? So I'll draw my little row, all 4 spots, since I'm going to arrange all 4 students. 4, 3, 2, 1, and what do we get if we multiply that out? 24. Okay, now let's take 4 students and put them in a circle. And just for fun, let's actually take 4 students. So let me get you 4. Come up here, take a chair. You won't miss any note taking. And I'm going to pause the recording, and we're going to talk about different ways of arranging you so that you're still in a circle. The important thing will be what makes it a different circle. If anybody has somebody different on your left or your right, it's a different circle. Even if you're sitting in a different chair, but everybody still has the same people on your left and the right, it's still the same circle. So it's not about what chair you're in, it's about how are you arranged compared to who's on your left and your right. So what we just modeled, we had 4 students come up to the chairs, and we discovered that with 4 students, they could rotate, and even though they were in different chairs, we got the same circle 4 times. There were ways that we could change who was on their left and the right, but each of those would repeat 4 times. I thought that was a lot more fun than just doing different colors in a circle, but I could have done it that way instead and then moved those around. So what we had, there were 4 factorial ways to put them in the chairs. But each one of those circles repeated 4 times, so I need to divide by 4 to get how many total circles. Now notice what happens when I expand that out. I have 4, 3, 2, 1 over 4. Since I had 4 people, the 4 cancels out my biggest number there, and I am left with 3 times 2 times 1, or 3 factorial, or 6 different circles that we could form from those 4 students being seated in the 4 chairs in that circle. So n factorial, if we're talking about how many ways to put them in a line, or n factorial if we're just talking about how many ways to fill those chairs. But if we're talking about how many different circles do we get, we need to reduce the factorial by 1. So let's put this in your formula list. The first one is if you have n and you are putting all of them in a row, it's n factorial. If you have 12 people and you're only filling 3 chairs, then it's not 12 factorial, it's 12, 11, 10. But if you use all of them, you can simply do it with the factorial. But if it's a circle, you have to reduce that factorial by 1. Don't really worry about the last formula yet. We'll come back to this slide after we do an example with circular permutations, and then we start to talk about distinguishable permutations. Okay, let's try a quick example. You're going to have homework problems that say in how many ways can 6 different items be arranged in a line, and in how many ways in a circle. When they ask you more than one thing in the same problem, you have to do something to label which answer is which. So we need to say linear and circle. If I'm putting 6 things in a line, what will I need to do for my setup on this one, Macy? So 6 factorial, you can write that out, 654,321, or you can enter that on your calculator. Has anybody done that yet? You could probably even do this one without your calculator if you really wanted to. 654,321, so that'd be 30, 120 times 6. What are you guys getting? 720? Okay, if we want to do it in a circle, how do we change the formula? What do I do for that one, Dylan? What? So for this one, what does that mean? So for this one, you can just write down 5 factorial if you want. If you prefer, you can write down 6 minus 1 factorial. So that's just going to be the 54321. So 20 times 6, 120. Give me thumbs up, thumbs down. Does that make sense? So if it says arrange it in a circle, you just figure out how many you have. And instead of that factorial, you drop it by 1 and do the factorial of whatever is 1 less. Okay, let's start to talk then about what distinguishable permutations are. So I've got 10 marbles up here. If these were like pool balls that had colors and numbers on them, or lotto balls that were going to be drawn that were almost all white and had numbers on them, and I could tell them apart, they would not be distinguishable. So if I had those numbers and I could tell them apart, I would have 10 factorial ways to actually arrange them. But some of them are going to end up looking alike. So that's going to be too many in terms of how many different ones that don't look alike. So let me just do one kind of random arrangement here. So everybody agree that's one way I could line the marbles up. And there'd be 10 factorial ways that I could do that if I could tell them all apart. But you know what? I can't tell those red ones apart. To me, if I switch those two, it still looks exactly the same as what I started. That's what I mean by distinguishable. They have to look different. So I wonder how many for just the reds. I could have this one first, right? How many choices do I have for which one of the reds I put first? And then once I do the first one, how many choices are left for the next spot? So I think I have 3 times 2 times 1 or 3 factorial ways that I could arrange just the reds that all look just alike. So kind of like when we had the students up here and we had 4 students, each arrangement of those looked the same 4 times, so we had to divide by 4. So for this one, we are going to have to divide by 3 factorial to take care of all of the ways that the reds could repeat and still look the same. But the reds are not the only thing that could repeat and look the same. I could take my blues and I could shuffle those around a number of different ways and they'd all look the same. How many different ways could I do the blues that look the same? So 3 factorial again. So since those all look the same, I need to divide that 10 factorial not only by 3 factorial for the reds, but also 3 factorial for the blues. Anything else I could rearrange and it would still look the same? The greens. And what about how many ways to rearrange those greens? 4 factorial since I have 4 greens. So I'd have to divide by 4 factorial to account for all of those repeats. And help me out here. Somebody punch that into your calculator for me, please. A little bit bigger than I think I want to do in my head. And who's got it? Kane, what'd you get? So 4,200. Anybody else coming up with that? So I would have 4,200 distinguishable permutations. So you see what we did there. So that's our other formula. If we have a total of n, big N, like we had 10 in this one, that factorial goes in the numerator. Then we look for things that repeat. We had blue ones that repeated. We had 3 of those, so we did a 3 factorial in the denominator. So if you have something that repeats and you have a of them, you put an a factorial in the denominator. If you have something different that repeats and you have b of those, you put a b factorial in the denominator. If you have still something different that repeats and you have c of those, you put a c factorial in the denominator. I do want to mention the book for some of these problems likes to do homework questions that have twins and triplets in them, identical twins and identical triplets. For those problems, you need to suppose that there's no way to tell them apart just by looking at them. Now, I know parents can tell their identical twin kids apart. I know when you're really, really good friends with identical twins, you get to where you can tell them apart. I know a lot of the time they do not dress exactly alike or fix their hair exactly the same way, and you can tell them apart that way. But to answer the problems in the book, you need to imagine you cannot tell them apart at all, that there's nothing that looks different about them. So not a twin problem, but we will try another example that uses this idea. So I'm going to take those letters in the word nonsense, kind of like if they're Scrabble tiles, and how many ways can I arrange them? Some will make words that have some meaning and some will just be gibberish. That's okay. But it's not going to matter, for example, if I put this end tile first or this other end tile first. When I line the tiles up, it's going to look the same. So first thing I need to do is count how many letters total I have in this thing. And 1, 2, 3, 4, 5, 6, 7, 8. So what do I do about the 8 letters total that are in this according to the formula you just wrote down? What? So we're going to put just 8 in the numerator, 8 factorial in the numerator. Does anybody see any letter that repeats in this word? Maddie, what about you? Do you see anything that repeats? And how many n's are there? So what do you want to do about those 3 n's? So we're going to put a 3 factorial in the denominator. And I suggest maybe like kind of label where that came from, especially if it's on a test. What if you just miscounted and skipped one of them or something? Then I at least know what you were thinking and how you came up with that formula. Taj, is N the only letter that repeats? What else repeats? And how many S's? So what do you want to do about the 2 S's? So we'll put a 2 factorial in the denominator for the 2 S's that repeat. Have we taken care of all of the repeating letters? What else do we have, Gracie? And how many E's do we have? So what do you want to do about the 2 E's? And numerator, denominator. So 2 factorial in the denominator for the 2 E's that repeat. Anything else that repeats? Okay, then we're done. Punch this in your calculators and let me know what we come up with on that. Molly, 1,680 distinguishable permutations. Does that make sense to everybody? Okay, let me pause this and I'll hand out your homework papers. Okay, on this one, it seems like, oh, distinguishable permutations, we get to use our brand new formula. And distinguishable, yes, it's related to this lesson because it says how many that look different. So if I put a white marble in this spot, it's going to look exactly the same as if I had put a different white marble in that same spot. So I'm not going to count those any different. I'm going to count those as the same permutation. That's the only part of this that really relates to this lesson. The difference is this is not just how many distinguishable permutations. It's how many distinguishable permutations with a restriction. So it's conditional plus distinguishable put together. And we're not going to learn an approach for those in this course. So because it's got two different things in there, you're not going to be able to end up using that formula. So we don't really know what we're supposed to do. What is our strategy on homework, on problems when we don't really know what we need to do? How do we approach it to start wrapping our heads around how we could solve a problem? What do we do, Evelyn? Well, we can write down the givens. What else do we often do, especially on some of these permutation ones? We just start drawing, okay, what are some of the ones that look like? Can we start to see any patterns? So I want to put these marbles in a row. And what might I start with? What do you want to start with, Samantha? Okay, Samantha says, okay, for our first one, let's start with white. Can I put white next? And meet the restriction? No, whites can't be beside each other. So everybody, what must go next? If I start with white, then, 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 and that's all 6 of them, right? So if I start with white, I can do that. If I start with white, can I do anything that looks different? If I switch the other 2 whites, it's still going to look exactly the same. If I switch 2 of the reds with each other, it's still going to look exactly the same. If I start with white, it's going to look like that. Only one option. Is white the only thing I can start with? What else could I start with? Okay, and then tell me, if I start with red, tell me the rest of the row. So if I start with red, it can look like that. If I start with red, can it look any different from that? Even if I switch 2 of the reds with each other, it's still going to look the same. So if I start with white, I get one way. If I start with red, I get one way. Is there anything else I can start with? So how many total? And choose your answer. See what I meant about we confuse ourselves because we try to use that new formula and we really can't. All right, you guys work on the rest of the set for the remaining time.